Hi everyone. In this video, I would like to show you how to get started with internet background radiation analysis. And of course, to reach that goal, I am going to use the data sets we have built by deploying the cloud telescope in order to capture cyber threat activity affecting the internet at large, at scale. So this is how to get started with this extract, transform, and load procedures, the enrichment procedure, how to get started with dataset analysis, the basic pipeline used to go from raw PCAPs to enriched data, and then to summarization data will all be discussed during this journey that should take a couple of hours to complete. All right. Let me start by sharing my screen and show you the details on how this is going to work. So sharing. Um, let's start in blank. I assume that you have no previous knowledge with the technical parts of radiation analysis. And in case we need to take note of the links, I will be using this document here. Okay, without further ado, let's get started. I assume that you are using Windows 11, Windows 10, any Windows will work. Um, Using Mac or using Linux directly should also work, but you will have to adapt accordingly to the situation. I have a couple of hints to inform so that you won't be caught by a Windows antivirus inspection, you won't get caught with the lack of tools. And to make this work, I also propose that we use Windows subsystem for Linux. So that's the first part. Before you get started, let's make sure that you can that you have Windows subsystem for Linux installed. One way of learning so is by visiting the Windows menu here, and then just search by to features, okay? Features, which means that we are trying to locate a certain control panel resource called turn Windows features on or off. And for sure, the features that are on or off on my computer are different than the ones that you have on your device, but pay attention to this dialog box here. It contains a range of items that you can enable or disable. In our case, because we want to run Windows subsystem for Linux, this means that you need to enable this one bottom up, let's say Windows subsystem for Linux, that's the first one that should be enabled. If it's not enabled on your computer, just tick it. Then you should also tick Windows Hypervisor Platform, which enables virtualization to run on Windows as a hypervisor. And you should also check the virtual machine platform. All right. Of course, if you're using a Norwegian version or a Portuguese version of the operating system, you have to translate accordingly to the situation. But these are the three devices or three resources that must be enabled. Otherwise, WSL won't work, and the experiment here will not work as well. I also have Hyper-V enabled, but that's related to using Hyper-V. That's not required. You can enable it if you want to further explore Hyper-V, but that's not related to the workshop here, all right? It's just the three ones at the bottom that really matter. I will press cancel. But very likely, if you enable these features and you press OK, which is what you should do, Windows will require you to restart. In that case, please restart your computer and get back to the video once you are rebooted. Otherwise, the upcoming commands will also fail to run. Okay? So you should tick the three of them, press OK, reboot, and return to the video. Now, assuming you are back with WSL running, I, I assume that you have no image installed. Let me show you. This is the Windows terminal. Like you can find it by issuing CMD. That's one way to get it, CMD. But it also means that I installed what is called the Windows terminal. This should be available at the Windows Store. Let me show you the Windows Store quickly. And why do we want that? Well, I need the Windows terminal because it allows me to quickly increase and decrease the font size, Windows Terminal. Windows 10, Windows 7 may have a slightly different version, but it's more important for myself because I am showing this to you. I'm recording my screen. In your case, as long as you get to Ubuntu, the way I'm going to show you, it works the same. But just in case, it's Windows Terminal provided by Microsoft. It's not one of those commercial tools out there. It's Windows Terminal. Doesn't need to be the preview version. Okay, so have that installed and then you open it and then you get to this screen. Okay, so this allows me to quickly increase and decrease the font size to make the recording easier. That's the reason we are here. Now, in order to run this for the first time, you need to issue WSL dash dash update. First, we reissue an update to ensure that your Windows has the latest version of this subsystem kernel. All right. So that is the reason you might not get this screen the first time you run it. Eventually, Windows will launch procedures that will update its internal resources to make WSL work. But if you keep running it, there will be a time where will be updated and you will get to this screen. So the question is, running this a couple of times until you see that it's already updated. No big deal running it multiple times. All right, that's the first one. Let's take note. Let's say so far we installed Windows Terminal at the Windows Store. We issued or installed WSL features on Windows itself. Search for features or the Norwegian Portuguese equivalent to it. And then now we issue WSL dash dash update first. And now we should be able to install our first virtual machine. Because if we list, like WSL list, there is no distribution found, right? So WSL dash dash list should show you an empty list of distributions. No big deal, no problem there. Let me just clear the screen. And then if you simply issue WSL install, it will work. It will install the default Ubuntu version that Microsoft wants you to install as a default choice. Otherwise, you can be verbose Ubuntu. So either by issuing install alone or Ubuntu, that should give you Ubuntu. Let me just copy this command so we can keep track of it on the document here. And then let's press enter. In my case, it's already installed in the sense that I already have the image downloaded on the cache, right? In our case, it might take a couple of minutes to download it from Windows Store or from Windows servers, the backend infrastructure for updates and stuff. But one way or another, you should get to this, enter the new Unix name or the new Unix username. In my case, it's Fabricio. That's the username you're going to see throughout this workshop, followed by a password. So the password here doesn't really matter, but you must issue a password. It will not echo, you can't see, but you must issue a password so that sudo will work from inside the virtual machine. Okay, and from this point onward, operation should complete successfully, installation should be successful, and then you shall see the Ubuntu prompt. As you can see, we were on Windows and now we are on Ubuntu, right? So this is actually an Ubuntu machine running this Microsoft modified version of the kernel, running Windows Subsystem for Linux version 2. That's what you should have. As a good practice, let's also issue. Let me clear the screen. So from now on, when you see me clearing the screen, I'm just pressing Control L to clear the screen. Control L, I will be using this quite substantially. And then let's issue a sudo apt update. Now we are updating the Ubuntu sources, right? I'm gonna press my password, typing it, and then we have Ubuntu repository is fresh so that we can install new packages. So the next one is sudo apt update, and that's all. We should not need an Ubuntu upgrade here because it's not the purpose of this workshop to update Ubuntu packages, all of them. We just need to refresh the repository so that when we install new software will actually arrive to our computer. Otherwise, apt install will not work if we don't get with this one before. All right, so this is the virtual machine, probably ready to go, only lacking a few libraries, only lacking a few resources out there. Now, let's talk about preparing your Windows host, of course, because as you can see, we have this shell, the Linux shell on the right, notes from Windows on the left side. Let's now open Windows Explorer. So this is my computer. Let me take you to the downloads folder. It's empty, right? We are downloading datasets on the download folder. This will be encrypted, and it will be encrypted for the sake of avoiding Windows antivirus trying to detect patterns that could resemble malicious activity, but it's actually network recordings. Pick up files containing suspicious activity. Should be harmless to your computer. But we need to find a directory where we can effectively work with this data and where we can handle it without this being disturbed by Windows running antivirus checks. If you don't do this, Windows will harm your work, will delete portions of the recordings as you work with them, as you read them, and as you write them. In order to cope with that, in order to exclude Windows default antivirus, if you have Kaspersky, if you have McAfee, it will be slightly different. But your goal here is to. And in this case, I suggest that you look for the keyword virus. So virus, right? Taking you to virus and threat protection. Let's open that dialog. Now let's see what we have here. We have virus threat protection settings. This is Windows Microsoft's default antivirus. Manage settings. Let's click on it. Manage settings. And then scroll down to the very bottom where you can find exclusions. So you should add and remove exclusions. Let's click on it. This is privileged. Windows should open a full screen dialog box asking you to elevate privileges. And this is where we add exclusions. Okay. The first exclusion will be related to the directory where we will be working with the data, or better saying, the first exclusion is related to the downloads folder as a safe measure. You shouldn't really need to exclude the downloads folder. Remember to disable this again in the future after you're done with the experiment. But let me add a folder. You see, I am clicking at the exclusion, folder, and then I am locating the downloads folder here. Then I select the folder, and you see it shows up there, meaning Windows will not disturb us when downloading data that could look like malicious data. And also, we need to create a directory in the root just to make things easier when typing commands. Let me click with the right button here. Let me create a new folder. And this new folder I will call IBR data, Internet Background Radiation dash data. Okay? IBR data as depicted. After we refresh, it should be alphabetically sorted IBR data. This directory should be protected at all costs against antivirus inspection. This one for sure will fail if you don't exclude it. So add an exclusion folder C colon IBR data. Okay? Now you have IBR data and the downloads. I also have a D colon backslash malware, which relates to situations where I download Mirai binaries, but that's not really in the scope for today. Now this is done. We are good to move ahead, and we should have the safe place in the hard drive so we can deal with data. We are going for this experiment, we are going to handle, let's say, less than 10 gigabytes of data, meaning you should be fine with whatever disk space that you have there. But for other data sets, much larger amounts of hard drive space might be required. Okay, so directories are okay. Let's go to, let me show you the Notion web page. So let me also take note. The shortcut is bit.ly slash IBR underscore Notion. So let me copy. So this is the main, what we call the main IBR cloud. Let's call it the main cloud telescope site. So this is bit.ly IBR under Notion. Okay, this is it. These details very likely will be part of the video description. So whenever I send you information, you should find it. And let's see what we have here. Let me see if I can increase the font size. Accept cookies. Okay. And this place contains lots of information. It's not only data sets. We have, or we have a growing collection of seminal papers. This is actually empty for now. I will keep adding seminal papers there, like Pang, Wustrow, Barry's publications, and the sort. Barry's thesis is there, so this is a great place to get started if you want to fully understand and have a, a picture in depth about network telescopes and internet background radiation analysis. Um, this place will contain related works in the future. And of course, whatever I wrote, whatever I published with Barry, Lucas, and Carla is already available here. So if you don't really understand the philosophy behind the cloud telescope or the theoretical foundations, don't start the workshop yet. Pause there, go read, and only return to this video when you are good to go. Places to get started. You can watch my 30-minute besides presentation. So this is to the wide public, broad public. Not really alone, it's not enough. Then you should definitely read the New York paper, the CloudNet paper. This is available both on the official resource at IEEE, but this requires a login and a password. But we also provide a Google Drive friendly copy. So let me open it in a new tab. And this is just to ensure that if you haven't read this resource, you should read it before moving on. Otherwise, most of what we are going to do today will not make sense. But read it, and when reading, pay special attention to the last column here, where we have future work, capture expansion. This is one possibility of future work, not part of the workshop for today. Dataset enrichment, this is for sure the most wanted unfolding that you can contribute with, either if you are researching at NOROF as a cybersecurity student, or if you're researching at the computer science department in Brazil, where I also supervise, or if you're just a researcher wanting more information about how to get started, dataset enrichment is the easiest and most relevant task that you can perform. Data visualization is also welcome, meaning if you have an idea of an analytical database or an analytics workflow that could help us to reveal new patterns in background radiation analysis, of course, feel free to explore the data visualization and analysis segment. I also have a couple of students researching there. So it's a good field, especially eventually if you have this data analysis mindset, if you're not that much into cybersecurity, but more into data analysis, surely this is a very nice place to get started or to explore. Okay, so that's the CloudNet paper. We also have the Salamanca paper, which is yet to be indexed on IEEE Explorer. Very likely next time you visit here, it will be indexed already. But for now, we have a Google Drive copy. And this one is very important for anyone wanting to pursue an analysis of data set number 2 and also anything related to botnet activity. So if that's your case, you should read this paper. Otherwise, you should also read it because it shows a nice methodology, a nice way to report data. Um, Not only we have like basic accounting through many tables there, but also we have application layer discussions, we have binary level discussion, or the binaries used to propagate botnets, in particular Mirai. We also have a discussion about the binary names that we were able to detect, um, the kind of HTTP commands these infections used to run, and also a relationship with the most likely CVEs that were exploited as a motivation, as a vector to such activity. So this work depicts a nice methodology that you can build by conducting further IBR analysis. So that's the Salamanca paper. Read it. Another one, this is mere curiosity, just in case you want to learn how we got to the telescope, how we conceived the telescope before even launching it. That's documented as our first paper in the field. Um, the cloud telescope as a keyword didn't even exist at the time. It was a cloud native framework to globally capture internet background radiation. And it's nice from a methodology perspective. It's a short paper, 4 pages. You can also read it very quickly. You can also see when we speak with the industry, when one of us, one of the research team members present the cloud telescope to the industry, the terminology we use to adopt is sampled, is given as an example by the You Shot the Sheriff talk that took place in March in São Paulo. And then the most important part, probably the one that we are going to use in this workshop, is the data sets, like the sets that you can use in order to step forward in terms of the understanding we currently have in terms of radiation analysis. So the first data set is the one that I am showcasing because it only contains 21 million packets, but it's a fully fledged experiment in the sense that we collected data from 26 different regions of the world. Therefore, that's where we are going to start. Many students will want to adapt this workshop to dataset 2. In that case, leave it for later. Do dataset 1 with me first, and only then adapt the mechanisms that we discuss for the second and the newly recently published dataset 3. Now, you see many links here, right? We have an official copy on Dataport at IEEE. We have Lucas Baylor's initial export, which is sound, it works nicely. That's where he extracted his bachelor project from. We have my extraction. That's the one that I'm going to show you. Um, don't click here because this is the post-processed version. I am actually showing you how to get there. Why? Because very likely you're going to rework the raw data sets that we have. And then you have the raw data set here. This is the one we are going to use on the video, how to get started with IBR analysis, this video. And therefore you shall click on this one. Let me click on it. By clicking, it should start downloading, like Google Drive's link like this. There is a problem with the network, don't worry. This is only related to the fact you can only download the package, meaning Google Drive is not willing to decode it for you, trying to sample or thumbnail, whatever. So just click on download, and then it says, well, we cannot scan it. Of course, we don't want Google Drive to scan it. Therefore, we are downloading it anyway. And then after doing so, you should see it starting here on the above box. 1.3 gigabyte should take a couple of minutes to complete. Meanwhile, let me get you back to the discussion. So um, the reason Google Drive cannot look for viruses is the fact that it's password protected. So when decompressing, you're going to use radiation, capital R, and an exclamation there, so that you can bypass antivirus inspection. That is the reason we are zip protecting or protecting, password protecting the zip file. Students having a Noroff account are also able to download the dataset straight from Noroff's public OneDrive. This is not really relevant for dataset 1, but for the dataset 2 is currently the only way. Meaning, if you plan to work with dataset number 2, you can leave this on the background because it's huge amount of files. You can either grab it. Let's say if you're not a student at Noroff, you can download the dataset from IEEE Dataport. It's almost 300 gigabytes, and you need to have a valid IEEE account there, a paid subscription or a paid institutional subscription to be able to download it. So currently, I have no easy way to make dataset 2 available to you. Things might change in the future. By the time you visit this, I might have found another way to make it available. But for Noroff students, you should click on part 1 and part 2 of the raw dataset, okay? Raw dataset will allow you to enrich it the same way I have been enriching it. In case you're not planning to enrich it, you just want to look at the dataset, look at the results, and publish stuff, upcoming stuff, in case you are an experienced researcher, then you don't need to enrich again. Then all you need is to download the rich version, enriched version, ready-made version in 3 parts. 3 parts because I split it into chunks of 150 gigabytes, each of the parts. In all cases, it's password protected. Do you need to download this for the workshop? No, you do not need dataset 2. I will not show it. I will not touch on dataset 2. However, if you are conducting botnet analysis, you might want to download this in the background while watching the video just because in the future you might want it. Otherwise, you just return to this page to get it downloaded. And now we have dataset 3. Dataset 3 is available at IEEE Dataport, the same, requiring a subscription. The raw version is available to Noroff students, and the post-processed version is also available to Noroff students. So that's the situation. Eventually, in the future, I might find a place to store. For example, this raw dataset is 35 gigabyte, and the post-processed version is 70, 80 gigabytes, including results. So in that case, it's up to you. In case you feel like exploring a long-term analysis of the radiation, I would say you start with dataset 1 for the workshop, then you compare with dataset 3, and that should be your work. Only in case you're touching on botnet activity, that's the situation where you want dataset number 2, okay? Once again, dataset 1, that's the one we are going to use. Dataset 3, long-term analysis. This is more and more relevant. It's getting more and more relevant. And dataset 2, if and only if working with botnet activity requiring the honeypot behavior. Okay? For now, we have just downloaded the first dataset from Google Drive or from Noroff account, whatever. It's the very same file. And then let's see what we have in the downloads. So downloads folder, we have the zip file there. If you open it up, you will see it contains a directory called E1, that's for experiment 1. And inside experiment 1, you have a lot of files containing the asterisk at the end indicating they are password protected, okay? So let's click on the folder itself. Let's extract it to the IBR data folder. Click on extract, whatever zip uh, program you are using there. Make sure that you are extracting to the right folder to not get caught by Windows antivirus. In my case, I am extracting to C colon IBR data. C colon IBR data, that's the directory we created minutes ago. Right? Now it asks for the password regardless your zip program there, even Windows default zip program will ask you for the password, and it's radiation, capital R, and remember it's an exclamation mark. So let me get this, add this to zip password is radiation. Okay, and then it starts decompressing. Shouldn't take more than a few seconds to complete. And as you see, we are working with a combination of Windows and Linux at all times. So let me let me close the zip program, see IBR data E1. Okay, experiment one. What you see here is a bunch of very small pcaps, compressed pcaps and metadata files. Okay, a lot of gzips and a lot of txts. This is what Lucas implementation of the telescope produces, and it's a number of chunks, of small compressed chunks, because that's how the telescope operates. Every 6 hours or so, every 4 hours or so, or every 24 hours at most, PCAPs will be uploaded to the bucket from the telescope, from the capture to the bucket, and they stay there. Every time a package, a zip package is uploaded, metadata is also uploaded. Let me show you this first part of the capture for this region. Look at the file name for these two files here. It's the same file name except the extension there. One is gzip and the other one is Windows text file or standard text file. It has AF South 1B. This means it's South Africa, the south region of the African continent. That's the only region or the only place in the African continent containing an AWS region as of today. And it has, so that's why it's called AF South 1. The fact it's B means it's availability zone B out of the three availability zones A, B, C. Irrelevant for our work. It doesn't matter which availability zone it comes from, but it does matter. It comes from AWS region AF South 1. Okay, moving on with the file name here. We have the IP number. Let me do the following. Let me get this text. Let me paste it here so it gets larger. So this is breaking it down. That's the region. B is the availability zone, irrelevant. This is the public IP. Let's just public IP. It's 13,245 and so on. And then we have a date or timestamp. So the remainder is not really relevant. But this is the public IP address, and this is the region it comes from, okay? Now, if we open this txt file, it contains AWS provided metadata. So this comes as a request that you perform on the virtual machine, and the virtual machine will dump its current state. Meaning the virtual machine itself was using non-public IP address 172.31.34.236. That's how cloud deployments work. There is a mandatory non-public IP address and an optional public IPv4 address. So this is mandatory and irrelevant to us. This is optional and it's very relevant. Okay, so those are the two places where you can extract metadata, either from the file name. That's what I do. I parse the file name and get it from there, but I could also query the txt file that is companion to each capture that we collect. I'm showing this to you because later I will show scripts relying on this information. Okay, now let's see the compressed zip itself, one of the chunks. Very small chunk, 34 kilobyte, just a couple of hours of collection. And then inside the zip file, we have the pcap. The pcap is like twice the size of the original compressed file. And we don't need to extract it. So let me just open Wireshark. Let me file open. Then we are going to browse until we find it. So C, IBR data, E1. That's the first pcap that we can, oops. Let me drag the header here. We have a bunch of pcaps there. Let me just see which one we want to open the one that ends with 20. So this is April 29, April 29, 7 or 5 o'clock p.m. And this is how radiation is displayed. The reason this is black and white and no detail is provided only relates to the way I tweaked Wireshark to work. Let me show you how this is done. I get here to preferences, so Wireshark, edit, preferences. One thing that is very important that you disable, otherwise your machine will get very busy, is name resolution. So disable MAC resolution, which is at the data link layer. Disable transport layer names, leave the standard ports, raw port numbers instead of names, and also do not enable, this is the one that consumes more resources, do not enable resolve network IP addresses as a default. Okay, all of these should be unchecked. This one is okay to leave checked just in case you resolve a name, it will use the internal DNS server. Okay, that's the standard. Also related to fonts and colors, I like to disable everything related to this, just to leave it basic. And then I use in layout, I use the stacked version instead of the detailed version. Okay, packet list, none, none. Meaning I just want the packet list. Otherwise, it will take longer. Otherwise, it will consume more CPU resources. Okay, I will press cancel because I didn't change anything. And that's what you have. A sequence number. You also have the source IP address. This is the very real public source IP address attacking the machine or probing our sensor. And then what you see next is a problem. Wireshark as our TCP dump recorded the local IP address effectively bound to the virtual machine. It did not record the public IP address, which makes data enrichment very confusing, right? So the first step in this journey will be to rewrite the destination column to contain the public IP address taken from the file name. It's easier to look at the source code that I created, the bash script, the very simple bash script that does the job, but just to explain to you why we have to do that. And that's where we get started with my virtual machine here, right? Let me clear the screen. And also with the pipeline that I have published on GitHub. In order to work with the ETL, I just have it here it in my bookmarks. So you are going to fetch this ETL from GitHub, this enrichment procedure. Let me document it on the Word notes that we are taking. So that's the place where you should visit. github.com, my surname, IBR-ETL. But to make things easier, this is the command that you're going to do. You're going to copy it. You're going to open the Windows terminal here. Let me go full screen. And then you will issue the following command. But in a second, how can we get from Linux into the IBR folder that I created? Windows Subsystem for Linux makes it very easy. You just have to cd into mnt, okay, slash mnt at the root. Then you have a link to the C drive and a link to the D drive. Here, over there, you can see them. So cdc, meaning I am entering my C drive, and then you should see the same folders you see from Windows, right? One of them being IBR data, right? So you cd into IBR data, and then you should see experiment one. You cd experiment one, and you should see all the decompressed files there. We can count it. We have 4,500 chunks, very small chunks, files there, half of which are TXTs and half of which are PCAPs. Let me clear the screen. And that's where you're going to operate data, okay? I will not download my ETL on this folder because it can get things confusing, right? 4,000 files, so let me get back to the previous directory. So now we have, let me clear the screen. We have just E1 as a folder. And then let me download git, that's the command, git clone, and then the website, the root of my project on GitHub. Okay, git clone, let me copy it before actually executing it. Back to the document there. So that's the command. And then cloning. All right, so from this point onward, I am using, okay, LL to just list files in column mode. So you have IBR ETL, a series of scripts, and you have the experiment one there. Same goes, just in case you are feeling lost, same goes if you just browse C, IBR data, you will see the two same folders there. So no big deal. Inside it, we have the scripts we are going to execute. In order to make it easier, let me browse them on GitHub. So here, as you can see, the project contains a folder named Other, and this folder contains accessory scripts, including the first one that we want, meaning most people out there, they don't need this enrichment procedure, but because you are my students, you are under my supervision, I suggest that you go through all the steps from scratch. Therefore, we will interact with the aggregation script. So that's the first step, dealing with aggregate pcaps. So this is the first step one or step zero, enrichment. That starts with aggregate pcaps. No big deal, very simplistic bash script that will read the file names in the experiment. This file name, it will extract the region, cloud region. This is Africa, right? South Africa, but let me scroll down. Let me show you the last one. The last one is US West 2, so the second region in the West region of the United States. So it will depart from the file names in order to get all files belonging to a same region into a single file. So see, this 1 month long experiment collected these many files, right? Before it turned to AP East 1. So these files should be aggregated chronologically, and they should also be compressed, and they should also get the private IP address depicted here, the private one, rewritten with the public, right? So the private address is meaningless to our needs. We are going to rewrite with the public IP address. That is performed in this script. Okay, first step, it's running TCP rewrite. Second step is to run region split. And the third step is merging all into one file per region, 26 regions, 26 files, and then compressing them in gzip just to save space. 4 steps, therefore. Ubuntu does not have all the tools that we need. So you see, we need TCP. Zcat is part of Ubuntu. No worries. TCP rewrite is not part of it. Easy way to find out what you need to install before you get started. Well, if you don't find this in advance, no big deal. I can show you. Let's show you how it will work if you fail to add the tools that are needed so that we can fix it. Let me show you. Let's get to the Linux box. Now we are in the IBR data root directory, let's say main directory. We are going to enter the experiment directory. That's where we have the pcaps, right? That's where we have the pcaps. And now we must be able to issue a command to execute aggregate pcaps.sh. This can be done in relatively to the directory where we are, or it can be done in full. I will show you in full reference. So it will be /mnt/c. Inside C, we have IBR data. That's the previous directory, but we also have a subdirectory called IBR ETL, right? So if I press tab, it should autocomplete. Inside it, we have a folder called Other. Remember? Other. And inside it, we have aggregate pcaps. So that's step one. This one will fail because I don't have TCP rewrite installed on my computer. But it's no problem. If it fails, it will just fail and you execute it again. Let me show you, just pressing enter there. It might look like it's running, but let's allow it to reach the end to see what effectively is showing up. Remember that you have to run this from the directory containing the pcaps, otherwise it won't work. Okay, so it might take a couple of minutes. I'm Control C. You see that many times you see during the logs or the output here, line 22, TCP rewrite command not found, TCP rewrite command not found, TCP rewrite command not found. That's because TCP rewrite is not part of Ubuntu. Let me show you on Chrome how you can quickly find. You could use apt there, you could use dpkg, but let me show you. Ubuntu and then TCP rewrite. Okay, Ubuntu and TCP rewrite. This will get you to the online manual pages, which is okay, how to use it, no big deal. But however, it's provided by a package called TCP replay. So TCP replay is the package that contains TCP rewrite. In that case, what we need to do is apt install TCP rewrite. That's the package. No need to add TCP replay. You see, TCP replay. If we try TCP rewrite, it won't work. Let me sudo just to show you. There is no package as such, but there is a one called TCP replay. So TCP replay. Let me copy the command, Control insert to copy it. And then TCP replay, the package is installed, which contains the TCP rewrite script. Let me add to the memory we are building. Okay, so eventually we should say that you should install TCP replay before dealing with aggregate pcaps. You see, that's why I'm switching the order. If we look at the source code once again, let's see if there is another command there, eventually tshark or something of the sort. Let's see, down there we have TCP rewrite for sure. Others are all variables, and Kadir is part of Ubuntu, MV is part of Ubuntu. So we have merge cap. Merge cap and later gzip. Gzip is part of Ubuntu, but merge cap is not. So same strategy. Ubuntu merge cap. Merge cap is a command that is provided by Wireshark Common. Okay, so in that case, let's see how we can install Wireshark Common. Sudo apt install Wireshark Common. Copying again to the transfer area, to the clipboard. And as you will see, because Wireshark is a graphical user interface tool, even the libraries will require a lot of graphical user interface stuff. However, we are not running a graphical interface here. It's just the libraries requiring 172 new packages. That's the price you're going to pay to have merge cap installed. You might see this message asking if you want to run Wireshark as root when capturing packets. We do not perform live captures here, so it's super safe that you simply say that you don't need to elevate privileges when running in monitor mode or whatever. So no is the answer. Because it's many packages there, it should take a couple of seconds to complete. And now, very likely aggregate pcaps will work. Remember, what we are doing here is aggregating per region and aggregating in such a way where we preserve the public IP address on the destination field. We replace the private with the public. So that you are now done. Let me just show you. You should see something like this as a result, like no problem, no error reported, but also nothing else. And then we can click the arrow up until we find MNT, C, IBR data, IBR ETL, the other scripts aggregate PCAPs, okay? Now let's have this executed. Now we see the screen moves a little slower, noting that it's really processing stuff. Because you are using dual Linux and Windows, let's get back to Windows Explorer. This is the original E1 drive, the experiment1 directory, right? If you scroll to the top, you might see, or eventually if you refresh here, while it's working, right? No problem. Let's split screen. It's working on the left side. Let me just refresh here. Let me find a way to eventually F5 should refresh. Yes. So now you should see a new directory was created by the script containing the intermediate files. Let's enter the newly created, automatically created aggregated directory. And inside it, you still see there is a range of PCAPs. So apparently it's duplicating whatever existed in the previous folder, apparently, but it's not actually. So in this case, let's look at the first of all, no txt here. It's just the compressed gzips, right? Let me open the first one. And then better, even better. Let me copy it. You don't need to do it. It's just to observe because it's taking a while to complete on the left side. Just follow me. Let me copy because I don't want locks related to whenever this script will delete intermediate files. Let me paste it to the desktop very far away from the work being done. Let me get to Wireshark. Let me click open. Let me get to the desktop now. And from the desktop, we are going to open it up. And as you can see, in this case, it's kind of the same intermediate file, but now the destination IP address is rewritten with the public IP address, right? That's what we wanted. That's a valid output. What is missing here is combining all South Africa files into a single one, all Brazil files into a single one, all Sweden files into a single one 26 times. That's the only step missing. But that's how the intermediate files look like. My script currently does not automatically delete these intermediate files, but later I'm going to show you how safe it is to delete this stuff once the basic aggregation script is done. So let me close it. Just let's say before closing, let's just randomly open this NTP probe that arrived to the sensor. So this is an NTP query, UDP package, having this data, probably probing the existence of network time protocol implementation on the sensor, which it doesn't have, right? But because it's UDP, you can even have access to the payload, which is decoded in hexadecimal and octets on the screen. Okay, so closing it up, on the left, we can still see computer is very busy aggregating and rewriting the TCP files. Let's get back to IBR data and then experiment one, and then folder aggregated. So you see this is growing. Look at the very bottom here. 400 items so far, and it keeps growing. We should have half of the 4,000 files as raw files there on the main directory here. So half of them are PCAPs, half of them are TXTs. So this procedure shall complete when it is 2,500 or so intermediate files. That should finish step one and step two of the enrichment procedure, aggregation procedure, if you will. Once more, looking at the source code will reveal what we are doing there. Getting back to the source code on GitHub, we are, for each file ending with pcap.gz, we are extracting the file name pattern. We are splitting by region in second, and we are merging into one file per region. Do you see that's merge cap is the key there? Merge cap looks at different pcaps and merge them chronologically. So it preserves the chronological nature even if you are collecting from many different pcaps happening at the same time in a distributed fashion. Last time I checked on my computer, it took like less than 4 minutes to complete. So that's probably the amount of time we are going to spend at this step. This is just aggregation. After the aggregation, we have at least 2 more steps to complete. Let me show you them. It's on the main folder for the project. It's 1, generate T-Shark CSVs. Second, enrich the CSVs. And third, summarize radiation. Um, those are the 3 steps that we have to do. And it's a surprise what I'm going to show you after step 3 is completed. It's like you are really going to enjoy it because it will save you a lot of time, especially when reporting your findings on the bachelor project document. I can automate most of the stuff. You just have to add your explanations there. The procedure goes on. By looking at it, we can see it's at the very last region already. At least for step 2, it's already at EU West 2 region. Therefore, very likely it's going to start the 3rd step or the 4th step very soon, and they are quicker to perform. Let me just send a message here. Just a second, let's see. I'm recording this workshop real time, so I'm not really editing the video, which I'm sorry. If you would like to edit the video, let me know, and then we can make it quicker for upcoming people. Now it's again at US East. It flashes very quickly, but it's possible to see it's there already. Let me go full screen. Eventually, by watching the video, you can pause and see what's going on. Now it's creating directories. So if we alternate to the aggregated folder, you will see that the script is creating folders, aggregating data into each folder. This is for the sake of splitting up one folder per region. And now it started step 3 where it's merging, meaning it's getting all files from the South African folder and merging the pcap there. No compression yet. For each one of the regions, it's performing the same stuff. So it's currently performing the 3rd region. And it should keep going on until it finishes US West 2. So it's in alphabetical order, but also it should, after this, as a step 4, compress each of the pcaps into gzip just to save space on your drive. Northeast one is one of the largest data sets, so it takes slightly longer to complete. In case you could be curious about my computer, just as a reference, this is a 12 generation i5. Memory is not really a big deal there. You'll see that it's not really consuming any relevant amount of memory. You see, it's just Windows 10. It takes less than 1 GB of RAM to compute this. It's actually a very dumb procedure, doesn't consume lots of memory. But it does require the CPU power that you can get. It's not multi-threaded as we learn in operating systems. There are people, I believe, Barry implements a multi-threaded version, but for now, this one is single-threaded, meaning it's only one CPU core that gets very busy at a time. You can get there by looking at the task manager. You will see that one CPU spikes every time. Eventually, Windows might find an average here to you, but it's mono-threaded. It's already computing South America is one, that's the São Paulo region. Now moving to the United States. And that's the last region. Now it's done with the pcaps and now it's compressing, you see? It's just getting each of these files and compressing them, applying gzip. Otherwise, it would be like 4 or 5 GB of data. As compressed data, it becomes 1.3 gigabytes. And then we can already start checking the sizes. It's 25 megabytes for South Africa. Asia Pacific, East 1, 31 megabyte. And then you can have a look or a glimpse of how busy each of the regions were probed during the experiment. But it's just raw analysis, doesn't tell much. It's not as precise as counting packets. Asia Pacific, so AP Northeast 1 took like 1 GB, so it's far far busier than the average cases. And from that point onward, compression should be much quicker. Anyway, this is being performed by a standard ordinary i5 12th generation. Once again, let's look at how files are showing up. IBR data, E1 aggregated. Those are the folders. These are the intermediate uncompressed pcaps, and these are the resulting pcaps. So you see AP Northeast 1 is the largest chunk that we have, the region attacked the most, let's say, and it compressed 3 times. So from 1.5 gigabyte to half a gigabyte, 3 times better. Or a compression of 3 to 1 actually. Okay, it's almost done with US, which are the last 4 regions, and finished. And then after finishing, it returns one step or one level in the directory hierarchy. And let's see what we have. So let's once again recap. We have the IBR data directory. IBR ETL contains the transformation and enrichment procedures, the scripts that I wrote from GitHub. We have the first experiment in its own directory. We have the raw 4,000 raw files here, 50% of which are TXT, 50% are gzips containing real data. Inside aggregated, we have the intermediate directories containing pcaps with rewritten destinations, right? Rewritten destinations. And we have the gzips containing the aggregated version. So people downloading the aggregated version, they are actually downloading this 26 items. You see, I'm selecting the gzips. It's 26 items, the very same 26 regions we launched the telescope on. Meaning you have the data set here. You also have it not really one step before aggregating in 26 different directories, and you also have it in its raw form here. So it's a huge waste. Just to show you that you can like confident that what you have done is the real deal, I am going to select every file on the main directory except the aggregated folder. Okay, we can do this on Linux or on Windows, doesn't matter. But just to make it more visual, I am pressing Shift Delete. Notice I am deleting 4,000 files except the aggregated folder, of course. And inside it, I am also deleting, because I didn't automate, this is commented on the script actually. I am shift deleting the folders, right? Because they don't really matter. They are just intermediate files. Staying therefore with the 26 files related to the dataset, one per region. Okay? So that's the dataset. That's the enriched version. Sorry, that's the aggregated version. Aggregated version. Let's fix it. Aggregated means it's aggregated in a way that makes sense for any student, for any researcher out there. It's not enriched. We don't have a control about countries or what latitude, longitude, attacking sources, attacking destinations. We don't have them. So my enrichment procedure will show you how to use Linux to get there. Now, in order to make this happen, let's look once again to the enrichment scripts. So the first step in enriching after aggregation is to generate a CSV out of the T-Shark or out of the PCAP using T-Shark. So this uses T-Shark to read PCAP and produce CSVs. Let's look at the source code. You see that I start by backing up whatever was done in the previous attempt. So if you keep executing this on and on, you don't need, you just need to execute it once. But if in case you execute it twice, it backs up the last execution. That's what the highlighted lines do. And then what we have here is actually a T-Shark execution. So we need T-Shark installed, and T-Shark is not part of Ubuntu. So if you execute it as is, it won't work. I can show you. Let me see. We are back to our machine, our Linux WSL variation. We have the aggregated directory there. Let's get into it. 26 files. And then we should run T-Shark there. If we simply run it, mnt C IBR data, IBR ETL, one generate T-Shark. This is bash, therefore no Python. It's just running it. Because there is no T-Shark, it will fail miserably, right? Why? Because there is no T-Shark as requested on line 17. Easiest way, you can simply, let me show you about how to use Ubuntu to this. apt cache, this doesn't need privileges, search T-Shark, right? And by searching T-Shark, you will see that a T-Shark package exists, Wireshark common exists, and others, right? Or even a meta package to work with forensics. That's what we just need T-Shark. So let me clear the screen, sudo apt install T-Shark. And then let me copy to our memories. And then we have it. Now it's installed. But before it, or while it, let me put it to execute. So this is the command. Let's add to memories. Clear the screen and let's start. Now it's opening each of the regions we have. each of the 26 packages we have, and it's producing a CSV, okay? First region is already done. Let me show you the results here. Notice that the script uses a name scheme that you can even make it better maybe, but it just outputs to output.csv.gz. Okay, that's what it does. It's a CSV file. And the old version of a previous execution was moved. This is just a silly backup, doesn't really mean anything, but that's the file that we have. And it's growing. It's growing as the script keeps adding to the end of the CSV a full export of each network event as recorded by the pcap structure. So let's see how the script actually does it. And this is where many students will need to adapt, meaning this is the T-shark line that does my export. In case you need anything other than I do, then you will have to do it another way. You'll have to change the parameters here to fit to your purpose. So this is where many bachelor projects out there are going to touch, and a cascade of changes will be required in the upcoming scripts, the two upcoming scripts. Let me find VS Code here. So let's see what we have. This does not allow me to quickly change the font size. So let's see Notepad. So Notepad help us quicker there. Okay. So we have time. Time is just a Unix utility to keep track of time. Let's do this while execution happens on the left side of the screen. Just make things cooler. Not sure if I can quickly disable a spell checking here. It's a Windows feature actually. So time keeps track of time. Then we have the tshark command. Then we have read the file used as an argument. So this is in a loop, 26 times it's going to work. Each of the times it will refer to a different file name. So that means read the current file name. Now this one relates to what you're seeing on the left side, resetting session. That means that T-Shark as a default will keep track of all TCP connections in memory, so that if a later reference is made to an ongoing connection, it will understand which part of the connection was initiated. Remember that TCP is a connection-oriented protocol. What -m does is that it will reset storing memory for each TCP packet at every 100,000 packets. So every time you see resetting session showing up, it means also that T-Shark has gone through 100,000 TCP packets. So millions and millions of packets there, right? So without this, my memory breaks. My computer, at least for dataset 2, it is unable to handle all the TCP data sequence, all the TCP connection tracking stuff. Sorry. The TAD is another feature related to time, how time is displayed. Or you can learn better by looking at the manual pages in T-Shark, but it's a required field there from the time when I was building the command. And then we are saying that we want to export the following fields, okay? That means from now on, we are specifying the fields that we want to export. The first field is a timestamp. We want to see the date and time where this packet was captured. The second field is, and this is using a standard TCP dump slash Wireshark syntax ip.src. You see that it took 4 minutes just for that step alone. Anyways, so this is the source IP address. This is the destination IP address. This is the TCP destination port. If this is exported, if and only if the current packet is actually a TCP. Otherwise, it's a blank. In case it's TCP, I also wanted to export the flag fields. Remember TCP, SYN, FIN, ECK, URGE, PUSH, and others. The stream of TCP flags were captured in my scripts just because I want to learn them, and they are exported if the packet is TCP. If the packet is UDP, we only want the destination port. We don't really need the source port. Eventually, it could be interesting, but not really. Most of the time, we don't account the source port. As you can see here, we also do not account the TCP source port, at least in my study. In case you want to study the source ports for whatever reasons, then you will have to improve the script and re-execute everything from this point onward. So you can aggregate, but you have to enrich each time you change the syntax here. Most of the times you won't need it. And then you have the UDP destination port, if it's UDP. If it's ICMP, we also want to learn the ICMP type, like ping, a pong, echo request, echo reply, and any other 15, 17 types of ICMP messages that exist out there. Whenever we are exporting, we want TCP Shark to kindly use a comma to separate. It could be a dash, it could be anything else, but of course CSV usually uses a comma to delimit the fields. Log level critical means that if we don't use this flag during this procedure, only during it, doesn't affect the results, you will see a lot of warnings. The warnings are irrelevant to our studies. Therefore, I suppress the warnings by using log level critical. In case you use T-Shark as shipped in Red Hat systems, you have to suppress this because this feature doesn't work there. Just saying for the case, in case you want to work with CentOS, Red Hat, Enterprise Linux, whatever, that won't work. But anyways, for now, for us, it works. For Ubuntu, it works. And then we say, well, the output will be the screen, except if you pipe it through another place. In this case, we are piping it to a compression tool, gzip. So gzip will read whatever arrives there, will compress it, and will keep adding. So -c concatenate at the very end of an already existing zip file without breaking it, without damaging the file. And then we keep adding, that's what means 2 times greater than in Unix, concatenate at the very end of the file and create the file if it doesn't exist the first time. Output.csv.gz. So this one compresses safely, keeps adding to the end of the file. In this case, it will keep adding 26 times to the end of the file. And you have to use 2 greater than here because otherwise it will keep recreating output with empty contents every time. So that would be big problem. So leave it as is, but that's the breakdown of the main command. Many students will have to adapt this to their needs if they want to investigate something that is not part of my export settings. You will have to start from this point onward. Okay, it's the last portion that is being executed there. Let me close Notepad and see what's going on. Almost there. Oh, actually, this is Europe yet. We are slightly far from finishing. It's not really US. Now we are going to Middle East. That's what it means. In case you're curious about this naming scheme, it's a good moment to show you up. That's related to AWS region names. There is a table somewhere here that shows you. So you see, US East 2 is Ohio in the United States, for example. US East 1, it's North Virginia. US West 1 is North California, meaning Seattle or the Washington state. not really DC. US West 2 is Oregon, and that's tricky because the US has 4 regions. Africa has 1 region in Cape Town, so it's AF South 1. Same goes with Brazil, it's SA, South America, East 1 in São Paulo. And then you have Asia Pacific in many places. You have Canada. This list contains more regions than 26 because there were regions released after we conducted the experiment. And also Stockholm is EU North 1. In case they one day open, in case in the future they open a region in, I don't know, Norway, it will very likely be called EU North 2 and so on. Um, and then that's how it works. Okay, and then T-Shark has ended. Let's see what it has produced. We have, let me refresh. We can safely delete the old file, 1 KB, so it's a backup there, doesn't make sense. But we have a 0.5 GB CSV. And inside it, we have a CSV that would open up with Excel, but don't do that. It will break Excel if you do. What we can do is use Linux, and it's nice tool set to explore the beginning and the end of the file. So let me show you how to read the CSV that we have produced. Because it's compressed, we are going to use zless. Meaning that you're running the compression version of the less command, which exists. Obviously, it's a Linux command. Zless output.csv.gz. So because it's text file, it outputs nicely to screen. And compare this with the notepad that I showed you before. The fields that you see on the right side match whatever you're reading here on the left side. Let's grab a standard TCP there. First packet. It started slightly before we published the paper saying, let's say we say that capture started May 1st, but it actually reports April 29. No problem, because we started the capture slightly before the beginning of the month, and we ended the capture slightly after the last day of month for dataset number 1. But this is the timestamp, followed by, as we said, should be the time. It should be source IP address. So source IP address, destination IP address. Therefore, this is the destination IP address. Then we have, if it's TCP, the TCP destination port, TCP destination port. TCP flags. The TCP flags is this burst of dotted pattern. In this case, it's a SYN request. Very cool. If it was an UDP packet, then the next field would contain the destination port. If it was a ping or whatever, ICMP message, then the last field would contain the type of it. That's why you see these 2 empty fields there, because in this case, it's a TCP packet or datagram. Now, look at this one. This is surely a ping coming from this IP address towards that IP address, the public IP address of the South African sensor. I don't really know it's the South African sensor. It's just because I remember you have to enrich this CSV to reveal the countries and stuff. But there is no TCP port. There is no TCP flag. There is no UDP destination port, but there is the ICMP type 8, which is echo request. So that's an ICMP message. Finally, look at this one. This one contains no TCP destination, no TCP flag, but also no last content or in the last field, meaning this is a new UDP datagram towards port 37,625. Right? So that's how you read it. and that's what it contains. So if you simply say like zcat, like this, now you're outputting to the screen, not paging, and you run a WC after it, piping with a WC, the number of lines will be revealed at the end of the command. It may take like a couple of seconds, eventually minutes to compute, because it's after all many million packets. It should have like 20 million packets, I guess. Let's see what we have there. Eventually, it's counting double lines. Yeah, very likely in a Windows format. Therefore, you are seeing for 40 million instead of 20 million, but it's actually 20 million entries. But the way Windows and Linux machine count lines is slightly different. Anyway, that's what you have after the the basic CSV extraction. Is this enriched? Not really. It's how can I tell how can I say if this effectively belongs to South Africa? Moreover, where is this coming from? From what country this comes from, right? In order to find you the answers, let me show you first a little bit of the libraries we use for enrichment. This is again on GitHub. Oops. Let's Lucas Telescope. And then we go to enrich CSV. This is the most complicated script I have for the enrichment procedure. I would say that delving into the details of this script is beyond the scope for this workshop, but let's look at the commands it uses. So it's Python. First of all, it's the first time we are using Python. It uses the sys library, which is part of the Python distribution. It uses GeoIP2. This is the library that allows you to translate IP addresses into countries, into latitude and longitude positions, revealing where the source is located to a certain degree of knowledge, to a certain knowledge degree. This is implemented via library. So using the library requires you to load the local database, meaning the library is not self-contained. You have to use a binary oriented database solver to translate IP addresses into their countries, the country they belong. That requires looking up into a table. I use the licensed version that Norof provides me access with of the library, but you should be able to use the freely available library. The freely available library works at a country level. That's the level that we want. Eventually a city level, but not to a certain resolution, and it works. And more importantly, by looking or by downloading the free version, you're always updated. My version stands still in time. So chances are that you're translating IP addresses into countries in a more updated manner. How to get the library? It's licensed. Even though the free version is free, I cannot redistribute it. You have to fetch it on your own. Let me show you how to do. GeoIP. Let me simply look for GeoIP library. Then it takes you to MaxMind. They are the company behind the library, so it's a professionally provided service. This requires you to create an account. I will click sign in, but you probably don't have a MaxMind account, so you will have to create one. I have mine, therefore I am using my password manager there. I will log on using my username and password. I will receive a second factor authentication code. Let me just look at my computer here for the code. Okay, it's a one time, so no problem pasting here. And then I have access to downloading the most recent version of the library. Where from? Let's look at it. Databases, so Geolite, okay, you can see on the right side, download databases. And then you have it, autonomous system numbers, CSV format for Excel-based queries, but we actually want the binary version, or the most updated binary version that we can quickly look at. And the Python library enables us to do so. So we want the GeoLite 2 city. GeoLite 2 city. You just click on download the gzip, and you should have it there on your download folder, okay? It's the city version that allows you to query up to the level of a city. You'll see later, this is 50% precise, not really precise, but at a country level, it's super precise. So in my downloads folder now, you can see that I have this GeoLite. It's a tar.gz. You might need WinRAR or another decompression tool. And then they have a folder there. And inside the folder, you have this MMDB. It's a binary format database, if you will. And that's the file, the only file we need to extract. So I'll click extract here, and I will extract it to the folder containing the radiation files. So it's C, IBR data, E1, aggregated. This one may take a while to open up. It's the aggregated folder. Let me download it to there. Pressing OK, it copies to the directory we are working, so it should show up here somewhere. You see GeoLite 2 city MMDB. Now, the script comes out of the box expecting you to have the commercial version. I don't know, in the future I may change this, but you must be ready to see that it might fail. So if you simply try to execute the script without adding the extra libraries, let me show you which extra libraries we are talking about. We are talking GeoIP as a library and the local file containing the database that is used for the translation. That's one. It's not really installed on this Ubuntu machine. AWS IP ranges is also not installed. So how can you install those libraries, right? One way of installing Python libraries is by adding Python pip. Python pip is not part of this Ubuntu virtual machine, therefore you should start with, well, first, let me grab the link here, add to the memory, to the Word memory document that we are building. Then we have to issue a command that will install pip. So sudo, I'm not really sure out of my head, but it should be apt cache search python pip. This is just searching, I'm not installing anything. And it should be, so that installs Python pip 2. That's not what we want. Very likely it's Python 3. Yeah, so it's Python 3 pip. Okay, so in that case, it's, let me clear the screen, sudo apt install Python 3 pip. Let me copy this to the clipboard, but just a minute, let's execute it. It requires a bunch of packages, so let me copy to memory document, and then let's accept it. Pip to be able to install accessory libraries on Linux to be able to work with Python. Okay, so let me clear the screen. Python is now contains pip as a plugin mechanism to enable inclusion of new libraries. So looking at the source code, we should be able to figure out the name of the libraries ourselves. Let's see. First one is called GeoIP2. So sudo apt, no, in this case it's pip python 3 pip. Is it so? No, it's maybe just pip. Yeah, so it's pip pip install GeoIP2, very likely. So it installs not only the requisite library that we need, but all the prerequisites leading to pip working automatically. Let's add to memory. pip install GUIP2. And let's say we also want AWS IP ranges. AWS IP ranges. Pip install AWS IP ranges. Let me copy, let me paste it on this nice console window. Sorry, I just opened up settings. Pip install AWS IP ranges. Default user installation, no problem. Downloading AWS IP ranges, successfully installed. So we are good to go. Now, you see that the script is expecting to run GUIP2 cd mmdb. Let's see. Let's just try to run the script to see it failing miserably. /mnt/c/ibr data /ibr etl. Now we are at step 2, enrich. Let me run it. It says there is a syntax error on line 4, and also it says that the solver is not really available. Oh, and moreover, this is Python, right? Python, Python 3 on Linux, Python 3. This is a Python script, not a bash script, so let me run it again. Now we have a more typical Python error. The first one was related to trying to execute that as if it was a bash script, which it wasn't. So let me clear the screen, do it again so you can see. There is no such file, GLAP2 cd. All we have here is a slightly different library name, the free version. So nano /mnt/c/ibr data, ibr etl, and then we have the enrich script.csv. In this case, we are commenting the commercial version and releasing or uncommenting the free version. And saving, Control X to save, right? So we have to nano and then Control to save, Control C to save. Sorry, Control X, I'll show you again. Once again, we change whatever we want here. Remember that you need to leave one of these commented, or you can even delete this, no problem, but leave this one working. Once you're done, Control X, Control X to save, and then Y meaning yes, okay? Then you're good to go, just press enter. Now we should be good to go. Let me try to execute it like you normally do. There is a hint on the source code saying that you shouldn't execute this script directly, but let me show you. Import sys, meaning this is actually expecting to read from the standard input. Okay, this is actually expecting to read from the standard input. But we can execute. If everything goes well, it should stay stuck in this command. So I pressed enter. Now it is stuck there and it will stay there forever. Why? Because this is a pipeline execution. Data is expected to get pipelined through the script. How do you sort it out? Like this. Control C to abort. And then you remember that you have a certain output CSV/GZ, so you will zcat it, output, and you will pipe it in the Python script, like so. I hope this is very obvious to you, but we are decompressing while outputting to the screen, then piping it through as an input to Python 3, and then the script will read it, right? If we stop there, data will enrich to the screen. Let me show you with less. Is it Python 3, right? I have a typo there. Oh, of course, it's Python. Yeah. So if we do this, it will output to my screen. It may take a while to initiate libraries, but this is actually at my screen. We don't want to have this on my screen, but I will take the opportunity, or let's do the following. Let me grab the first 20 packets, head 20, and then let me put, don't need to replicate this. This is only to enable me to explain to you while it does on the real data set or over the total amount of data. This is just a sample that I'm going to use to show you. So this should be very quick. Let me see if we have what we have in the sample. Yeah, sample is good. Now let's do the real stuff. The command that you really have to execute is this one. So you're going to enrich, you're going to compress, that's a pipe, and then as an output, it will be output, like, let's use a name like enriched dot g dot csv, because it's still a CSV file, but it will be compressed. So that is why. And let me copy this command before we get started. Let me put it there. So this is the command that you're effectively executing. And we can also keep track of time. In this case, we can add time there just to see later how long it took. Time. Okay, time, zcat, the output that we already have, pipe it through Python 3 to enrich, and then we will compress whatever results we got to a file name called output enriched or rich, whatever, .csv.gz. So let it run. So now I press the enter once, no problem. You can press enter many times, doesn't hurt. Procedure should have started. We should see signs of activity here. C, IBR data, E1, aggregated. We should see at least a new file arising. It's called output enriched. It's 0 kilobyte because it's being created as we speak. We can also check, like we can even open an accessory window. Let me issue CMD here. We can, you see this tab, find a way to start Ubuntu. So I start Ubuntu, it's the very same virtual machine, and then I run agetop. Agetop shows you enrichment is running, so we can leave it running. It's also compressing the output, and you see like scripts starting and stopping the enrichment procedure, launching sub operations there. Memory is not a problem. It doesn't consume not even a 1 gigabyte of RAM, so it will work on any computer. Let it run, okay? Meanwhile, let's look at the sample that I collected before, which you don't need to extract, but you just need to see and learn. Aggregated, there was this sample.txt. Now, what is the enriched? What is the enriching procedure? Currently, the enriching procedure is this. Let me show you the same packet that we worked before, right? You see there is a timestamp there. There is a source IP address. This remains the same. There is a destination IP. This remains the same. There is a destination TCP port. Remains the same. A TCP flag remains the same. The UDP destination empty because it's not UDP. The ping type or the ICMP type empty. The source country ISO code. Source country ISO code. Source country normal name, usual name, standard name. Source city, if possible. Otherwise, it will result a null that I translate to unknown. See here, for example, it's unknown. We don't know the city. So you have to handle that as an exception in Python. I already do this. So this is the source latitude. This is the source longitude. Okay, so you can pinpoint on a map if you want. This is the attacked country ISO code, South Africa, ZA. That's the name of the country, South Africa. The name of the target city, Cape Town. The latitude of the target city, the longitude of the target city, and then using AWS IP ranges, the library that I showed you, we can recover the destination cloud region. Not always it's so obvious that AWS region in South Africa will be AF South 1. Think of the US. They have 4 regions there. So many many regions leading to the same country. Therefore, we need AWS IP ranges to cope with this part of the resolution. And that's it. That's what the enrichment procedure does. Let's imagine you want to add the TCP payload to investigate botnet activity. That is not revealed by my pipeline. My pipeline, you can clone it, but you will have to find a way to export the payload. I am not interested in the payload in the standard pipeline. So you have to enrich it. You have to find which flags of the tshark command you want to add to the script, and then you will have to edit the enrichment script to work as you want, as you need. That's what it does. Okay, actually, the enrichment procedure took 4 minutes to complete. Time flew. And then we have it done, right? After 4 minutes of operation, no errors being reported. Now let's count the number of lines. You will see that we don't have 40 million entries. We actually have 20 million entries or so. In this case, it's zcat, output enriched, right? And then we are going to WC. Funny joke, but that's the command just to make sure that you can count the number of packets at any moment. And let's add it to the memory here. Now back to instructions, we have almost 21 million, right? Almost 21 million entries. That's why we often say we have 21 million events registered. Now thinking about why we had 40 million packets before and 20 million now, it's because we started to capture much before May 1st, and we stopped slightly after the month of June had started. However, during the enrichment procedure here, I trim everything that is before May 1st and everything that is after the end of the last minute of May. Let's see, let's use command tail. Is there, so zcat, now let's get like tail, or let's get the first 10 entries. You will see that they start exactly May 1st, even though our initial data set doesn't. Right? So we trim whatever does not belong to the month of May out, even though it would be legitimate and interesting traffic. We can also check the tail. This will take longer because we have to scan through all the 20 million packets and only extract the 10 last events. But you will see it will stop at 2 seconds to midnight, starting June. So this is May 31, 11 p.m., 59, 58. Right? So that's where capture stop. That's the last relevant packet arriving for the experiment. Even though we captured more, we are trimming. This is in script 2. You have like the time frames there. All right. So that's the result. Now, will you load this into Power BI? Will you work with Excel? Will you work with writing your own Python pipeline starting from there? I don't know. However, the bonus that I have to share with you is very, very nice. Will help a lot for those who are writing reports in LaTeX, meaning I wrote a script that will go through the final data set, the byproduct generated by this effort, and it will create aggregation tables. in LaTeX format, right? So let me show you. This is actually very cool. Let's look at the source code first. It's summarize radiation. That's the name of the script. Contains a lot of aggregations there. I believe it has no requisite. Yeah, it's just ordinary Python using ordinary libraries. No pandas, nothing, just myself and standard programming there. I can't brag about the beauty in this code. It's not really the best practices in terms of programming. However, it does the job, and it does the job interestingly well. So in this case, let's see it's waiting. Is it working, waiting as an input from the standard input? Yes, input sys. So what it means is that we are piping through zcat. We are zcat output enriched, so decompressing it to the output. And then we are calling Python, then MNT, C, IBR data, IBR pipeline, summarize radiation. If we do like this, it will output results to the screen. Not really useful. We need to output data to a text file so we can work with that text file later. So I suggest that you output it using, of course, the greater than output redirector to results.text. And I will show you why and how. Results.text. This should take 10 seconds or so. Let's see. Should be very quick. Later, if you want, please have a look at the source code. It's very, very interesting to see how you can extract aggregations from the accounting script, like just by loading each entry in memory and categorizing them by protocol, by port, by country. You can not automatically, but very easily expand this to any other need that you could have. It's more dynamic than meets the eye. Okay, so it's going through the entire valid enriched data set and it's summarizing from there. It actually consumes what? A minute or so to complete? Let's wait. Okay, it's done. Let me show you how it's going to work in a second. So in order to make this very fun, see how you can do it. I will take you to Overleaf. I will take you to the standard bachelor project proposal template, just because that's the most fresh template that I have. That's the template that was shared by Barry recently. So let me copy it. And let's say IBR dataset 1 results. And let's copy it. All right, so let me get back to all projects. Not sure if I should remove, okay, so it's tagged. All projects. Where are you? Oh, that's the mask that I'm using there. So IBR dataset 1 results. Let's open it up. Let me show you here how fun this is once again. You click on upload, select cancel, select a file, and then you get back to C, IBR data, E1, aggregated, and then you have results.text. Click on it, upload it. Just before you include it and compile it, just get back here, see it's LaTeX at its best, scroll down and delete the non-LaTeX data that exists at the end. So I have some Python structures there that I'm using for testing new stuff. This is not really LaTeX, so this will break if you don't delete, but you see, that's the last table, and then you just select everything below the last table. okay? And delete it. Let's say if you're using the very same version that I'm using when recording, you should have 851 lines of useful LaTeX data. And then you get to your main source here. Let's choose a chapter. Let's say we want to describe it in whatever will be the primary data set there. So let me locate where it is. So this is the data set. And then you simply come along here and you say it's either input or include, right? So it's input results. And then you recompile and see magic happening. It might take like 30 seconds, 20 seconds to have this compiled. After all, it's a bunch of tables with result data that you're going to see. See, it takes like, I don't know, 20 seconds maybe to compile, but just wait. Wait and see. All right. So let's scroll down. Our document has like 28 pages. Let me download it first and open it up on the browser so we can uh, use more screen area. Okay, then we scroll down. And then you see that among this primary dataset chapter, we start seeing the results. There is even the basic commands are there. The transport layer distribution is shown, is depicted on table 1. We saw, as we counted before, 20 million, almost 21 million packets, out of which 16 million are TCP. That's experiment number 1. 3 million, or almost that, refers to ICMP, and UDP is almost 2 million. And the percentages are also automatically calculated. Unknown packets are matching nothing of the sort, 679. So we even deal with uncertainties there. When looking at the unique radiation sources, the number of different IP addresses in the source field, we saw 250,000. Pretty cool number for such a short experiment with such a low number of sensors. The number of radiation destinations, meaning how many different IP addresses were used by my sensor fleet when we deployed the telescope, 112, even though it was only 26 sensors. Some of them had to recycle, had to rotate, had to refresh IP addresses. Therefore, we saw 112 different IP destinations. That's just it. It's not really the most relevant information that you can extract, but it's information. Now, the number of packets arriving to each of the cloud regions using AWS terminology, EU West, this is London. London got almost 10% of the radiation, where the standard mean is like 3.80, very around this number. This is an average case. This is an average case. But anyways, it got 10%. So why? The question is why? Can you investigate why? Do you want to investigate why? How can you apply this rationale to dataset 2 and 3, right? Is this a burst, or is it something common? Like that region is always more attacked than the average. We don't know. But that was the sample. That's what the sample reveals. And the least probed region was US East 1, the oldest AWS region. Only 1% of the traffic, 1.5. When speaking about the radiation targets, but not by AWS region, but by ISO code country, we see that the US has got 13% of the radiation. That is quite a lot, but remember that the US has 4 different regions. So it's expected it gets 4 times the baseline radiation, which is the case. Now, Great Britain, UK, they really got quite a lot for a single region in a single sensor, 9% of the traffic. This is using ISO codes, and they have the very same table using names, friendly names. So this is just for you to choose which one you want to use when reporting results. And Brazil was the last one here with the lowest number in this case in the top 20, but it's 26 region. This table is designed to work as top 20. You can change it. If you just change a single line or a single argument in the aggregation script, which only takes 5 minutes to complete, you can have this as a top 10, as a top 1, and then the percentages will follow accordingly. If you create a top 26, then you will see all the regions. If you create a top 30, top 100, you'll get 26 regions as well. Brazil was the least attacked region in this case, and followed by Sweden. Very interesting. Two countries, very low attacks in terms of packet count. When looking at cities, London was the most attacked. This has to match necessarily the distribution found for GB, Great Britain. Tokyo was the second most. This is also related to Japan here and the region there in Asia Pacific, of course. And then we have 5% of the cases where GYP was unable. They were able to find a country 100% of the times, but not really the city it was coming from. So we don't know. Meaning from this point onward, we don't know. Then whenever it was possible to find a city, it was Zaragoza, Frankfurt, Hyderabad in India, and so on. Okay, so that is what you can find at a city level using GOIP. I would say it's for curiosity, it's fine, but it's not really relevant until now. I have never thought about a reason where a city would be of interest. It's, after all, country level analysis. This is radiation sources, though, so this is not really related to the attacked regions. Did this answer the question? Who is attacking? Where are the attackers coming from? They're coming from the US in 31% of the cases, from the Netherlands, 15% using ISO code. Let's move to the friendly version down below, which has the same data but with friendlier names. China third, UK, Russia, these are the countries that attack the most. Why is it the Netherlands in second? I leave up to you, but very likely you heard me speaking about this. It's probably because the Netherlands has lots of anonymity services, including VPN services and related. Therefore, that's one explainable reason for the Netherlands. But the remainder, it's open for a study case on why. Attacking more than 1% was Singapore in the last position. Below Singapore, they don't contribute with more than 1% of the radiation. That could be considered a nice cut line. Now, the sources in terms of city, unknown in 8 million packets. So we cannot really state what was the most attacking city because in many cases we don't know. But London comes second with 10% of the radiation, where it also figures as the attacked region. Very interesting phenomenon. I would say this is biased. This is simply because we happen to listen to a sensor that was occasionally catching that. We have to listen more sensors for more time to see if it's a trend or not. But anyways, that's what we got. Top 20 TCP ports as the attacked ports. Telnet, 9000, SSH, web, HTTPS, fairly even distribution, but surely TCP 23, the telnet port, is of interest. And it's like 3% of the data set refers to it. Now the flags. I should mask this with fixed length characters. Very easy to do with TextT on LaTeX, but anyway, I can do that later. But then you can see the flags or the dotted mask usage to define the flags. I have a thorough documentation about this in my degree report. You can look at it later. However, we can see that most of the packets are SYN packets, 80% of the cases for all TCP cases. Reset flags also prevalent with 17%, SYN plus ECK, only ECK, null scan, Christmas scan. So you can see all those behaviors, even though below SYN and ECK, it's just a bunch of very rare situations where those flags happened, but they arrived anyway. So we captured and we accounted. Speaking of UDP port, attacking ports, attacked ports, probed ports, 9,000, 12,000. There is a discussion about this on the papers, on the CloudNet paper. 50% of the UDP traffic was aiming at port 9,000. You can read on the CloudNet paper the reasons why. And it's also related to gaming server implementation as a curiosity, as one of the vectors. So that's the kind of knowledge you can find out. Speaking of ICMP message types, we have 2 million packets belonging to echo request, the ping, 158 echo responses, which is the pong, but we never issued the ping. Therefore, it's very odd that we are hit by pong, by echo responses, without requesting a ping. Anyway, it's there. Also, odd types like 13, 17, and 3, they were rarely seen, but they were captured and accounted. Now, this is the TCP distribution per AWS region. We never published this kind of data, and it could be interesting. When only looking at TCP, what shows up the most? In this case, it's EUS2, this is London region again, 6%, followed by EU Central. Okay, it's just a pattern. UDP radiation target. So when looking at UDP only, we know that 50% of the data set belongs to attacking London. Anyway, it's there once again, but just tailored to UDP radiation targets. ICMP radiation targets per cloud region. It's fairly even, but there is a trend towards Asia Pacific South too. Now looking at the TCP radiation sources, so the countries attacking only using TCP, United States, Netherlands, United Kingdom, no real emerging pattern there. This pretty much follows the standard distribution seen before. However, Russia is slightly above here, China is okay. But now look at the UDP radiation. Like when only looking at UDP radiation, which countries are attacking the most? It's the US, it's Germany, United Kingdom, Singapore slightly above. We can also see Finland. We can also see Russia, China, Hong Kong, and so on. Okay, that's interesting. That's something to be used for people researching the geopolitical influence. Now, look at ICMP. ICMP is 85% of the times conducted by China or Chinese-based hosts. Why is it? We need to dig this further, for example. And the US comes in second with only 5% of the full data set. So this is very interesting finding that needs unfoldings. Now, the top 20 TCP radiation destination, looking at the country level, but only for TCP, US, Japan, and India, 14% for the US. UDP, same reading, just looking at the destination for UDP traffic, only UDP traffic. Once again, we see the UK. Actually, it was the UK, the most hit sensor. No other interesting pattern out there. And now looking at ICMP radiation destination, India was the most attacked country. So China was the most attacking country for ICMP, and India was the most attacked one. So just in case you have students out there who want to investigate geopolitical influence, ICMP is deeply related to denial of service attacks. Not alone, but it is. So it deserves consideration. And that's it. That's what you can learn by implementing the pipeline that I wrote. For the next steps, I would say try to do the same with dataset number 3, not dataset number 2, because that's too big. Deal with dataset number 3, and then when you're comfortable, go dig further in dataset 2, but then it might take, let's say, 6 hours to do the same job, 10 hours to complete the same job. However, one way or another, you are going to have to implement it, especially if you're developing or studying botnet-related studies. Well, having said that, we are done with this workshop. I hope you have enjoyed. I hope you have liked. I hope you have understood the contents I wanted to show you. I hope that you are able to reproduce my experiment. You are able to compare results, and you're able to see that the enrichment pipeline works, that you can inspire yourself designing new pipelines based on this one, fetching it, building it, changing it, improving it, and releasing on GitHub so that in the future I could be using your enrichment scripts instead of yourself using mine. So that's my best wishes for this research field. All right. Thank you very much for your time. Thank you for staying for so long. Hope you have enjoyed. And reach me if you want to learn more, if you want to discuss advanced aspects, feel free to reach me and we will have a meeting to discuss variations of the topic. All right. Thank you very much. See you on the next time. Bye bye.